All right. So the next speaker is the last speaker of this session. So Taylor Hutchison, who is talking about near-infrared spectroscopy of galaxies during reionization.
Hi, thank you. Yeah, thank you to the organizers for letting me give a talk. I'm really excited to share what I've been working on this past year. Let's just dive in. We have heard a lot of really great talks already, kind of talking about why we care about the epoch, that's why we're all here, and then also motivating why the Lyman Alpha mission line in particular is really useful for probing into the epoch of reionization. So just to kind of springboard off of that, and then very quickly dive in, we're going to talk immediately about kind of some of the limitations that come from using Lyman Alpha. So Lyman Alpha is a resonant line. It's subject to scattering, and is also heavily attenuated by neutral hydrogen. So often the redshift you would derive from Lyman Alpha can be hundreds of kilometers per second redward from where the systemic or true redshift for a source actually is. And you can kind of see this in this example here where I'm showing you this gorgeous asymmetric Lyman Alpha profile, and the blue dashed line is the redshift we derive using Lyman Alpha, which you can see is offset from where the systemic or true redshift for the source actually is. And you can quantify what that offset looks like with the equation on the bottom left, but mostly this would probably suggest to you, correctly so, that there is some kind of need for systemic tracer, something that's not attenuated by neutral hydrogen or outflows and can represent the true redshift of the source. Now, in the rest frame ultraviolet, there are a number of lines you could potentially use for this. This is an example, Lyman Galaxy composite spectrum from Alice Shapley's work, and you can see really strong Lyman Alpha emission, and then we have these red lines highlighted, which are just a variety of nebular lines that can be used to trace the systemic redshift. Now, I do color carbon-4 slightly differently because it's actually a resonant line, and so it doesn't necessarily always trace systemic, but for the most part, you get the idea. And if you really want to pick a particular line for follow-up, if you have Lyman Alpha already, you would probably have the best bet with carbon-3, just because it's often the second brightest line after Lyman Alpha in the rest frame ultraviolet for these high redshift, low metallicity, high ionization galaxies, and also it's pretty ubiquitous for galaxies at these redshifts. But just in general, all of these UV metal lines are really powerful probes of what's going on within the stellar populations, give you insight into the ionization in these sources, and also tell you a little bit about the chemical enrichment in these galaxies. So all of it's really powerful. Now, here's just an example of some of the detections that exist at redshift greater than 6. There are more than what I'm showing here as far as detections, but there's not much more. It's actually really hard to get detections of lines other than Lyman Alpha, just because they're so faint by comparison, and we're also in the near infrared at this point, so we're plagued by skylines if you're working from the ground. Something else I want to highlight here is all of these gorgeous detections I'm showing you, they all have Lyman Alpha associated with them. And so for the most part, we use Lyman Alpha to give us an indication of redshift, and then we follow up to get our actual systemic tracers. Something else I kind of want to highlight here is you kind of get this beautiful variety of lines. You can have carbon-3, nitrogen-4 and helium-2, or carbon-4 and O3. And so you can kind of learn a lot of different information depending upon the kind of lines that you have. So what have we learned from the UV detections that we have so far at these redshifts? Well, the star-forming galaxies that have been detected, for the most part, seem to have these subsolar metallicities, really hard ionizing radiation, and for the most part, young stellar populations that might include binary stars or an IMF that extends up to 300 solar masses. However, we could definitely use more UV detections from more galaxies, and ideally, lots of lines detected in a single galaxy to increase our constraints. So this is kind of where my work has started, my current work is coming in. So in order to increase the number of spectroscopic detections for galaxies in the epoch of reionization, I've kind of started this program. It's pretty simple and straightforward. We are building a sample of galaxies from the literature that have Lyman Alpha previously detected at redshifts 5 to 8. There's a priority sample, which I'll talk about in a second. And then we target the rest UV emission lines. And ideally, we would get detections of one or more of these. You can measure the systemic redshift from that, compare to Lyman Alpha, get insight into the kinematics of the galaxy, and then compare it to all of your available photometry and all of your observations, compare to ionization modeling, and walk back any kind of inferred galaxy properties that you can. Just kind of piece together the narrative of this epoch and the galaxies that we're finding a little bit better. As a note, detections of more than one of these lines in a particular galaxy would significantly increase constraints on your stellar population properties. And actually, even non-detections can provide really valuable information. And if you're curious about what that means, you can check out my 2019 paper where we had an upper limit of silicon-free. So to kind of highlight what the program kind of looks like, using Keck, the Keck telescope and the MOSFER instrument, which is a gorgeous near-infrared spectrograph, you can kind of leverage this really beautiful sweet spot in redshift where you go from like redshift 6.8 to about 8, where you have some number of UV metal line emission in the J band, while simultaneously having some number of those lines in the H band. So the really cool part about this is, for a single galaxy, for example, with this spectrum at redshift 7, you can get 5 lines with these 2 bands if you were able to get all these detections. It is important to note that a lot of these lines might be really faint, but even upper limits can provide really useful constraints when comparisons to modeling. So for this work, we were awarded 8 J-band nights in 2018 to 2019 by work led by Rebecca Larson, which you've already heard about. This program was kind of a secondary science case for it, so we targeted redshift 5 to 6 sources. And then for this J and H-band program, we were awarded 4 nights in 2020. We're still working through all the data and processing. Shout out to Rebecca Larson for an amazing job with the data reduction, and stay tuned for that awesome work. So to show you some of our preliminary results, I first want to show you this beautiful serendipitous O2 detection at lower redshift. It's gorgeous doublet, the kind of detection we wish we could get at higher redshift, but sorry. So what I really want to show you though here is you're seeing these really bright emission spikes in the center, this bright white light, and then you have these negative traces above and below. This is just a unique characteristic of data that come from instruments like Mossfire, where they employ a dithering technique to take data. So real things will look like this. So here are some of our tentative detections of UV lines at redshift greater than 5. This is preliminary, just as a note. And I could tell you what we think these lines are and what redshift they are, but honestly, I want you to stay tuned because I am actually more excited right now about a particular emission line, and I'm going to spend the rest of my talk talking about that line. So we have a carbon-4 detection at redshift 7.5, which I am way too excited about. It's really cool. You can see we've detected both parts of the doublet. So what you're seeing here is Mossfire 2D spectra on the top with this very faint detection. You can see the negative traces. And then we have our extracted 1D spectrum on the bottom. Now, another really interesting thing about this galaxy is it actually already had Lyman Alpha detected. And so the velocity offset from Lyman Alpha is about 120 kilometers per second, which is interesting because that implies that either Lyman Alpha is being blue shifted relative to carbon-4, or carbon-4 is just more redshifted than Lyman Alpha. So it'd be great if we had some kind of, spectroscopic tracer and a systemic tracer for this galaxy. And conveniently, we do. This galaxy has actually been very studied in the past, including my 2019 work where we got a carbon-3 detection for it. So this is just a stat sheet from that work. Feel free to go check out the archive paper for this. I'm not going to cover this in this talk. But using carbon-3 as our systemic tracer, we can then compare these lines relative to systemic. So the carbon-4 velocity offset from systemic is about 200 kilometers per second, which is pretty large, and especially large when you're considering the fact that the Lyman Alpha velocity offset for this galaxy is actually only 88 kilometers per second. So this has been a really interesting conundrum that we've been encountering. A lot of interesting questions come out of this, right? What would be causing this offset in the first place? Why are they tracing different, why do they have different offsets? And why is carbon-4 way more offset than Lyman Alpha? So there are some possible implications off the cuff we could think of. It could possibly be something to do with, stellar carbon-4 contribution, maybe something to do with the optical depth in C3+, possibly something to do with the alpha velocity of high ionization gas. And there could definitely be more reasons. As it's a resonant line, there's lots of complications. So stay tuned. If y'all have any theories, I would welcome them. It's really exciting. But just looking at the line fluxes now and ignoring the offset for a second, if we compare it to our carbon-3 detections, you can see here what I'm showing you is carbon-4 over carbon-3 on the y-axis. And then we have IRAC color on the x-axis, where at this redshift, IRAC color is a proxy for the O3 and H-beta equivalent width. And you can see with all of these models that we're using, colored by metallicity, at the top right corner is where our points, like our observations, occupied, which indicates this really high ionization and really low metallicity, with these gray lines being 10% solar. This is really interesting, even for the stellar populations on the right-hand side, our single stellar populations with an IMF that only goes up to 100 solar masses. We seem to have this extreme region for these models that it occupies. So now that we have all these lines detected, we can expand our modeling and go deeper and try and really pick apart what we're seeing here. But just to also compare to some previous measurements for some clarity for y'all, what I'm showing you here on the right-hand side now is the carbon-3 equivalent width on the y-axis and still IRAC color. And you can see that with those measurements, it's pretty good agreement with what we have with our carbon-4 measurement, less than 30% solar and an ionization log U greater than negative 2.5. So we're still seeing this story of this really high ionization, low metallicity system. Now, it is important to mention that AGN might be a factor here. We could possibly have a weak AGN, and that's what we're looking at. There is a weak nitrogen 5 detection that was suggested from some GRISM data in 2016, although it wasn't seen in the 16-hour Mossfire spectrum. Or it could be a fractional contribution from an AGN, and a young, massive stellar population providing most of the ionizing light that is still yet to be seen. We're going to be continuing this analysis, so stay tuned. I'm really excited to see what comes out with this galaxy. And yeah, that's it. So I will leave out my summary, and I will take questions.
Right. Thank you, Taylor. So time for questions.
It looks like we have a number here. Do we have constraints on helium-2 in this galaxy?
Oh, such a good question. Sadly, no. We know that helium-2 is pretty hard to model just in general. I would be uncomfortable placing an upper limit without actually trying to target this line. And this galaxy is perfectly placed in redshift where, using Mossfire at least, helium-2 does not fall in any of the bandpasses. So ideally, we'll target this galaxy using James Webb, all the wood. But no, I can't get any helium-2 right now. So I would expect it may be really strong, but I'm also just hesitant because it's so hard to model.
All right. So the next question is from the Joris Wistock. So do both lines of the carbon-4 doublet have a consistent velocity offset from systemic?
Yeah, that's a great question. They do. I can go back to that so you can look at it. Yes, they're both offset. They're perfectly separated based on the redshift you derive. I did get this redshift from the first line just because it was stronger, but they are well offset. There is an interesting shape to the second line, which might have certain implications, which I don't feel like I should go into just because we don't have a good enough resolution for this, but they are offset the same amount.
As a kind of a related question is, how accurate is the velocity spacing of the carbon-4 doublet compared to theoretical expectations?
That's a good question. Honestly, I'm surprised that it is at this large offset. I would have expected the velocity offset for this based on at least what I've seen observationally. Theoretically, I would assume if you add in any kind of radiative transfer because the resonant lines, you could probably get some crazy stuff. But based on what I've seen observationally, I would expect it to be on par or within errors of Lyman Alpha. Like at any other high redshift galaxies that have carbon-4 detected, in addition to Lyman Alpha and another systemic line, they're within errors. So I'm surprised by this. I don't know if that actually answers your question. But.
Right. So the next one is probably the comment from David Sobral. So let me know if you want to directly compare. I was just checking that some AGN LAEs sources at redshift 2 to 3 have blue shifted Lyman Alpha in relation to carbon-4.
That would be fantastic. Yeah, I'll get in touch with you because I want more examples to look at.
So maybe I think we have one more question. Time for one more question.
Sure. Yeah. Do you have a plot of the Lyman Alpha and carbon-4 line profiles together? It would be interesting to see the shapes, as this could inform what is going on. It is not surprising to have Lyman Alpha fill as close to line center as allowed by the escape physics.
That's a great question. I don't have a plot with them on top of each other, but I don't have a plot with them on top of each other. But that is a really good suggestion. I will make one that shows that. Lyman Alpha is very much asymmetric in this galaxy, with a signal to noise of over 10 from the 16-hour Mossfire spectrum by Inte Zheng. But yeah, no, it's a fantastic question. I will look into that.
All right. So now all of the questions are running out. So maybe the last question. Okay. From the John Chisholm. What is the carbon-4 equivalent width? Also, what is the carbon-4 doublet flux ratio?
That's a great question. For the equivalent width, I've not yet calculated that. I'll be using broadband photometry to approximate that like I did with carbon-3. So stay tuned for that. But as far as the flux ratio is concerned, it's pretty close to 1, but the first line is larger. I've seen examples where the carbon-4 flux ratio is about 1.3 with other sources that kind of match at lower redshift. It seems to be about that for this source as well. So stay tuned. We'll look more into that.
All right. So now So I think it's time. So yeah, all right. So thank you, Taylor, for a nice talk, and let's thank all of the speakers in this session.